When we play video games, we are used to see many elements on the screen. A game scene composed by 3D or 2D objects, an HUD layer, an in-game menu, and so on. Usually all these elements are not rendered all together, but they are rendered in different frames. At the end, all these frames are merged all together in a specific order, making in this way the final scene we are used to see on the screen. But what are concretely these frames? Technically, these kind of frames are called frame buffers, and today, in the C++ 3D game tutorial series, we will face them in detail. As first thing, what is a frame buffer? Frame buffer, also known as render target in DirectX, can be defined as a special texture in which it's possible to render primitives, points, lines, or triangles through the various draw functions provided by the graphics API. That means we can render whatever we want inside it, from a really complex 3D or 2D scene to HUD or in-game menu, and so on. Since the frame buffer is a texture, it can be used in various ways. For example, it can be applied over the surface of a 3D object. Let's take a 3D model of a monitor, and let's suppose this monitor has two materials, one for the monitor and the other one for the screen. If we render our space shooter game created in the previous tutorials in a frame buffer and then we use it in the screen material, we can obtain this kind of result. Today, we will implement this use case, but as we have already seen at the beginning of this video, many other use cases of frame buffer exist, and we will face them, in particular the ones related to HUD and user interfaces, in the next tutorials. Let's see now concretely how to implement the frame buffer, and since we are using DirectX, let's call it render target. As we have already said, render target is nothing more than a texture. For this fact, we can easily get and extend our texture class in order to support it. Here it's necessary to make a clarification. As we have already seen with the swap chain, a specific render target must be settled in the graphics pipeline through the usage of the onSetRenderTargets function of the device context, in order to render the various primitives. But render target is not enough. It is also necessary to set another special texture that is called depth stencil buffer. We have already seen that the depth stencil buffer is used to determine what pixel must be drawn or discarded based on the depth information. If we don't use it, we will get this kind of result, where in some cases rear parts are shown over the front parts, problems already faced in the 18th tutorial. So we have to extend our texture class in order to support even the depth stencil buffer. We can extend the texture class by adding a numerator called type, composed by three values, normal, render target, and depth stencil, defining a new constructor in which we pass the size of the new texture and the type as parameters, and to define the new size of the texture we will create a new class called Rect, where properties like left, top, width, and height are available. Finally, this new type of texture should be created through a new method in the texture manager that we can call simply createTexture. At this point, we have to make our frame buffer demo by creating two classes. The first one that represents the main scene and the window called frame buffer demo, for which we render the monitor mesh that shows the render target on its screen, and the secondary one, a copy of the space shooter demo class that we can call mini game, in which we render the demo inside the render target with the help of a depth stencil buffer. Since frame buffer demo class represents the main scene and the only window available, all the events fired by the window and input systems must be handled inside this class. Then, in order to execute correctly the space shooter game, all the various window and input events should be redirected from FrameBufferDemo class to minigame class, through the usage of the various event methods like onCreate, onKey, and onMouse events. Once all the classes will be settled up, we will obtain this result. Very well, we have gathered all the necessary information to start the implementation. Let's start by adding a new filter and let's call it frame buffer demo. Let's create a new class with the same name. At this point, we can copy and paste the contents of bump mapping demo class inside the frame buffer demo class files. Let's rename bump mapping demo with frame buffer demo by pressing Ctrl F both in header and C++ files. Let's go to main C++ file and let's see if the new class works. And it works. Well, now let's start to extend our texture class. As first thing, let's add the new constructor, and to do that we need to create the Rect class. So let's open the Rect header file available in the templates folder. Now let's open the math filter, and here let's create a new header file called Rect. Let's copy paste the content of Rect header file of the templates folder. Now let's come back to texture header file, and here let's start to add the new constructor. As the first parameter, let's add the Rect parameter, size. As a second parameter, let's add the type of texture. As we have already seen in the introduction, we have to add an enumerator called type. Here let's define three values: normal, render target, and depth stencil. At this point, let's use it in the constructor. Very well. Let's add the corresponding attributes. And let's implement the constructor. And other two methods, getSize and getType methods. To implement the constructor, let's call the superclass constructor method used previously to pass the texture file path. Since here we are not using any file, let's simply pass an empty string. Now we have to create a texture in DirectX from scratch. We have already done this previously in the swapChain class for the depth stencil buffer. Let's copy-paste that snippet code. Let's set the various attributes like width and height. The format of texture is based on the type of texture. If we have a normal or render target texture, we will set normal RGBA format color. In the other case, for the depth stencil texture, we set a format that defines 24-bit for the depth information and 8-bit for the stencil data. Now we have to set also the bind information that defines the effective type of the texture. The bind flags talk on their own. In the render target, we have to set also a shader resource flag. This flag allows to use the texture inside shaders. Let's create the texture. Now we have to create the so-called resource views that we can define as handles or pointers to the concrete resource. In this case, the concrete resource is their texture created with create texture 2D, and now we have to create the following resource views. The shader resource views, already encountered in the previous tutorials, that must be created for both a normal and a render target texture. And this view is used by the API when we have to set a texture to a specific shader. Then we have the render target view, used by the API when we have to set the render target into the graphics pipeline. And as last view we have the depth stencil view, used together with the render target when the OM set render targets function is used. At this point, let's release all the resources, taking care to check the validity of the pointers. Very well, now we can go to Texture Manager, and here we can add a method called createTexture. Let's add the same parameters added in the new texture constructor. The implementation is straightforward. It's nearly identical to the one used for the texture from file. Very well, the render target and depth stencil textures are ready to be created. At this point, let's create a new class in the frame buffer demo filter and let's call it minigame. Here let's copy paste the content of Space Shooter Game class. As we have already done before, let's rename the class. To be sure that everything works fine, let's test minigame class. And it works! Now let's create the main scene with the monitor mesh in frame buffer demo. So let's add the mesh attribute and two materials called monitor material and screen material. Then in onCreate method, let's create them as we have already done previously. Let's set a different texture to the screen material to see if the screen shows the image properly. In the render method, let's set the materials. Remember that the order in which the materials are settled is important. As last thing, there is a little fix to apply to the mesh class. When the material currently selected doesn't correspond to the material of the face we are currently considering, we have to increment the index offset, and only after that we can continue with the loop. Let's see if it works. And it works. Now let's rotate off 180 degrees in order to have the monitor in front of us. Good, now let's rotate the light accordingly around the y-axis. Very well. At this point, we can start to fix the minigame class. As we have already seen in the introduction, we have to remove all the references related to window, input system, and swap chain. Let's leave the various event methods that will be called by the frame buffer demo. In the C++ file, there are some errors to fix. Let's start with the first one. Here we need the size of the viewport. This size is not more defined by the window, but by the render target. So, let's start to add the render target texture, and even the depth stencil texture. At this point, let's get the size and let's set its attribute in the viewport. Now we have an error related always to window size, in this case to set the projection. Since today we will not change dynamically the size of this render target, let's simply move the projection update in the onCreate method. Let's move on and let's delete all the methods related to Windows and input system classes. Let's leave only the methods related to Windows size. Now, let's define a new Rect attribute called Windows size. Let's go to on mouse move and let's use the Windows size just added. At this point, we can start to create render target and depth stencil buffer. Let's set a resolution on 1280 per 720. Now let's go to render method, and here we should set the render target and depth stencil buffer into the graphics pipeline, but we don't have any suitable method that allow us to do so. So let's go to device context class and let's start to implement three methods. Clear render target color, clear depth stencil, and set render target. We have already implemented these methods for swap chain. Now we simply overload them in order to support even render target and depth stencil buffer. Before to proceed further, let's set the size and type attributes in the texture class constructor. So far so good. Now let's go back to Minigame C++ file, and here let's clear and set our render target and depth stencil buffer. Good, minigame should be done. Let's go to frame buffer demo header file, and here let's add a minigame attribute. Now for each window and input event, let's call its corresponding method of minigame class. Let's start with onCreate. Here let's remember to set the initial window size. So let's implement a suitable method in minigame class. At this point, let's start to set the render target of minigame class to the screen material. To do so, let's add a getRenderTarget method in minigame class. Good, we have only to call all the various event methods of minigame class. Let's call on update method of minigame class before the update of the frame buffer demo class. In this way, when we have to render the monitor mesh, the render target to show on the screen is already prepared with space shooter content. As a last thing, let's switch from monitor scene to space shooter scene by pressing the ESC key. In the end, let's clean a bit the render method of minigame class by removing all the last swap chain references. And let's see if it works. And it works. That's all for now, folks. Today we have seen the frame buffer in detail. I hope you enjoyed this video. See you soon. Thanks for watching.